Gases behave ideally at low pressure and high temperature. When we describe the particles in a gas as a collection of particles, we're saying that there's no interaction between the particles. So there's no attraction or repulsions between them. That happens ideally when the pressure is low and the temperature is high. If the pressure starts increasing, you can think about the volume going down, because the relationship between pressure and volume it's not proportional, right? If one is increasing, the other one is decreasing. So if the pressure starts increasing, you can think about the volume decreasing. If the volume is decreasing, the gas particles are getting closer to each other and interactions can happen. Same thing with the temperature. If you have a high temperature, the gas particles are going to be moving around constantly. If the temperature starts to go down, then your particles are going to start moving slower and they can find each other and have attractions between them. All of the things that we went over about gases, it's assuming that your gas particles behave ideally, that there's no interaction between them. So using the same properties that we went over, like volume, pressure, amount of gas, and temperature, we have an equation, which is your ideal gas law, that relates all of those properties. Okay? With just one equation, which is this one right here, we can find the relationship between all of the properties that you have in that equation. For example, I'm solving my equation for volume, and I have number of moles, R, which is the gas constant, and you have the number here, and that gas constant, it can have a different number if the units are different. But for our calculations, we're using volume in liters, pressure in atmospheres, amount of gas in moles, and temperature in kelvins, which means that that should be your constant right there. So solving my equation for volume, I end up having this. And with that equation, you can check the relationship between pressure and volume, which is your Boyle's law. You have volume here and you have pressure down here. So as this number gets big, since you're dividing by that number, as that number gets big, the volume gets small. So they are indirectly proportional or not proportional. Okay, if one is increasing, the other one is decreasing. And with the same equation, just solving for the volume, you can check, or you can actually look at it in that notation right here. It doesn't matter which one you're using. You can check the relationship between volume and temperature. In your equation, temperature is multiplied by R and N, which is your number of moles. Okay? So if this number gets bigger, your volume will get big also right here. Okay? So big temperature, big volume, because they are directly proportional, right? If one is increasing, so does the other. And that's Charles' law. And then you have Avogadro's law, which is the last one, relationship between number of moles and volume again. So here, your number of moles is right there. You're multiplying your number of moles times the constant times the temperature divided by the pressure. But that number of moles is multiplied by, so if that number gets big, your volume is also going to increase because they are directly proportional. So we have our new equation, our ideal gas law, and we can use that equation to do some calculations, and this is the first one. So whenever you have a calculation, you should check the numbers that you're given, and with that information you should be able to identify which equation you need. So far we have used Boyle's law, Charles' law, and Avogadro's law. You have examples with all three of them. So this will be the first problem where you have to use the ideal gas law. So I have here amount of gas. Gas is nitrogen, and I have 0.845 moles of nitrogen. I have a pressure, and I have a temperature right there. And you're trying to calculate a volume. So this is your equation right there. You're finding volume, you have moles, you have temperature, you have pressure. The value of R, it's always the same. So you just need to plug in the numbers in your equation. And with that, you can calculate the volume that you need to find. So volume will be equal to your number of moles times the constant, and I'm going to write down all of the units that you have in your constant, which is liters times atmosphere over mole times kelvins, times the temperature, which is 315 kelvins, that's right there, and all of that is divided by the pressure, which is 1.37 atm. So you have 0.845 times 0.0882 times 315 divided by 0.137, and that's 15.9. And your units, mole cancel out with mole, kelvins with kelvins, and you have here atm with atm. All of the units are canceling out besides units of liters, which is a unit of volume, and that's what you're trying to calculate. I have 3 problems here. I'm going to do one of them, and then I'm going to give you the answers for the other 2. You're trying to find out volume right here. You're trying to find out pressure in this one, and in this one you're trying to find out volume. Those are the 3 things that you're trying to calculate. So I'm going to do the first one, and then I'm going to give you some information about the third one, which is the more complicated one. So first one, I have right here moles of helium. I have a pressure. I have a temperature, and you're trying to find out volume. That's your equation, and solving for volume, which is something that you already have in the previous page, will give you that. So you have your number of moles of helium times your constant times the temperature in kelvins, all of that divided by the pressure, which is 0.97 atm. And that will be 3.0, 2 significant figures because of that number right there, 3.0, and that's liters. Mole cancels out with moles, Kelvin with kelvins, atm with atm, and you have unit of liters. The second one, you have a volume right there, you have amount of gas, and you have temperature. So you need to solve this one for pressure, not volume. There's your equation, you need to solve for pressure. whenever you get your answer, you can check with that number. And then in the third problem right here, we need to do some steps before finding the final answer. In this problem here, you have a mass, okay? That is a mass of CO2. You have a temperature in Celsius, and you have a pressure in millimeters of mercury, and you're trying to find a volume. So if you want to use PV equals nRT, your ideal gas law equation, you need units of moles, you need units of ATMs, you need units of kelvins. So before solving this problem to find out the volume, you need to convert all of these numbers, that one to ATM, and you have that in your notes somewhere, that one to kelvins, and that mass of CO2 you need to convert to mole of CO2. Once you do all of your conversions, then you can plug in your numbers in your equation, solving for volume, and you can get your final answer. And the answer for that problem should be 16.1. So you can solve your problems, and then you can check your final answers with these numbers here. Something really quickly, and these are like just definitions, okay? So standard conditions are conditions that we can use and control to compare what's happening between different gas samples in this case. But this works with other things, not just for gases. So STP means standard temperature and pressure. In standard temperature and pressure, it's a specific value for temperature, which is 273 kelvins, a specific value for pressure, which is 1 atm. So under standard temperature and pressure, any gas sample, if you have 1 mole of the gas, the volume will always be the same. So I'm going to show you with the calculation so you can see, and then we're going to go over this a little bit more. So STP temperature is 273, your pressure is 1 atm, and the number of mole, because we're looking at a molar volume. If it's a molar volume, it's amount, the amount is 1 mole, like the molar mass. The molar mass, it's the grams that you have for every mole of a substance. So molar volume is the volume that you have for every mole of a gas. So you have your equation solving for volume. Again, you have here 1 mole of the gas, you have the value of the constant, the temperature, because its STP is 273, and the pressure, because its STP will be 1 atm. So your units, everything should cancel out besides liters, because that's what you're trying to get. And that's going to give you 22.4 liters. That number right there, it's the molar volume of a gas sample if you have 1 mole of the gas at 1 atm and 273, that should be kelvins. So right here I have 1 mole of helium, 1 mole of neon, 1 mole of carbon dioxide, and you can keep going on writing down 1 mole of any gas. And if your condition of temperature and pressure are at STP, you have a temperature of 273 kelvins, a pressure of 1 atm for all of them. You should have a molar volume that is equal to 22.4 liters, because you have 1 mole at 273 and 1 atm. Now, density of a gas at STP, you already know, temperature and pressure, standard conditions, okay? So we can actually calculate the density of a gas using this equation here. And this equation comes from the combination of your ideal gas law and the molar mass. Okay? You can work it out if you want, but you don't have to. The density is directly proportional to the molar mass, and you can see that in your equation because molar mass is right here. So the bigger this number gets, since it's multiplied by, the bigger that number gets, the bigger this one here is going to be. So we can calculate the density, and in this case, we have a problem to calculate the density for hydrogen gas. We need that temperature in kelvins, which is going to be 293, right? 273 plus 20, that will give you 293. We have a pressure that is in ATM, and what we're missing is, because we need pressure, we need temperature, that's our constant, but what we're missing is the molar mass. Hydrogen gas is a diatomic molecule. So it's not just H, it's H2, one of your 7 diatomic molecules. So molar mass for that one will be about 2 grams per mole. So we can calculate 113 times 2. That's divided by your constant times the temperature in kelvins. And I have 9.41. Let me check. Divided by 0.082 times 293. Yes, 9.41. And you're calculating a density, so let's check the units. ATM cancels out with ATM. Mole from your molar mass cancel out with mole in your constant. Temperature right here, your kelvins cancel out. And the units that are not canceling out are grams and liters. Grams over liters. So grams per liter is usually the unit that we have for density of a gas. Grams per milliliter for liquids, grams per cubic centimeter for solids, and usually for gases, the densities are given in grams per liter. So with this equation, you can calculate the density for any gas sample if you have the pressure, the temperature, and you can find out the molar mass using the periodic table, okay, which is what I did here with hydrogen. And you should remember that as the molar mass of your gas increases, so does the density. If you have an unknown sample of a gas, which means that you don't know which gas you have, you can actually use the ideal gas law to find out the molar mass of your gas sample. And with your molar mass, you can have an idea, or you can actually identify a gas sample. So to find out the molar mass for a gas sample, you have problems similar to these ones here. So let me check what you have in your problems, and I'm going to do one, and then you're going to do the other one. I will give you the answer. You have right here a volume, because that's milliliters. You have here grams. You have here a pressure, and you have here a temperature. So if you recall, for your equation, PV equals nRT, from this equation you have a volume, you have a pressure, and you have a temperature. What you don't have is that. Now let's see why that's important. If you want to calculate a molar mass is grams per mole. That's the definition of molar mass, right? If you have 1 mole, how many grams you have in that 1 mole for that specific substance. So molar mass is grams per mole, and if you check your problem, in your problem you already have the grams. It's right here. So to find out the molar mass that you need to calculate in this problem here, you need to find out the moles because you already have the grams. For you to find out the moles, that's the only thing that it's missing in your ideal gas law right here, because you have the pressure, you have the volume, and you have the temperature. Not in the correct units, but you have all of them. So 248 milliliters, right, you can convert that to liters because in 1 liter you have 1,000 milliliters. 745 millimeters of mercury, you can convert that to ATM because 1 ATM is the same as 760 millimeters of mercury. And you can get your kelvins because 28 plus 273, that's going to give you your kelvins. So you have all of the numbers that you need in this equation to solve for moles. Just that they're not in the correct units, so I'm going to write it down. That's 0.98 ATM. And that should be 248. So pressure 0.98 atm times the volume, which is 0.248 liters, over 0.082 times 301 kelvins. And remember that what you're trying to get here is the moles, because to get the molar mass you need grams divided by the moles, and you already have the grams here. So you're using the information that you have for your gas sample to find out the moles, and then finally calculate the molar mass. So that will be 0.98 times 0.248 divided by 0.082 times 301. That's about 0.01 moles of your gas. I'm rounding 0.0098. That's just the mole. So now you need to find out the molar mass. And to find out the molar mass, you have your grams divided by moles. And I have like 44.2, something close to that number, and that's grams per mole. And grams per mole, because you're finding molar mass. And then you can do this one, which should give you something close to 4 grams per mole. You have your grams right here. You have volume, you have temperature, you have pressure. You need to convert all three of them, similar to what we did in this problem here. Once you convert all of them, you can calculate the number of moles, and then you can find the molar mass dividing your grams by the number of moles.